What if everything you've been told about the beginning of the universe is wrong? The Big Bang, the moment of creation. Time zero, the instant when everything exploded into existence from nothing. What if none of that is true? What if the universe never began at all? Einstein figured this out. He had equations that showed a universe with no beginning, no end, just an eternal cycle of expansion and contraction. But he abandoned it, called it his biggest blunder. And for a century, physicists forgot about it. Until now. Because the data coming in from our most powerful telescopes is showing something impossible. Something that matches Einstein's forgotten theory perfectly. The universe might be eternal. And that changes absolutely everything. Let's start with what everyone thinks they know. The Big Bang. About 13.8 billion years ago, the universe began. All of space, all of time, all of matter and energy compressed into an infinitely small point. And then, bang, expansion. The universe inflated faster than light. Space itself stretched. Matter-formed galaxies emerged. Stars ignited. And here we are. That's the story. That's what's in the textbooks. But there's a problem with this story. A massive problem that most people never hear about. What happened before the Big Bang? You might say nothing happened before because time itself began at the Big Bang. There was no before. Time started when the universe started. But that's not an answer. That's just restating the question. If Jimmy began, what could trigger Big Bang? And here's the deeper issue. The equations that describe the Big Bang break down at the moment of creation. They give you infinities, infinite density, infinite temperature, infinite curvature of space-time. When your equations give you infinity, it means they've stopped working. They're telling you they don't apply anymore. So the Big Bang theory doesn't actually explain the beginning. It explains what happened after the beginning, but the beginning itself, that's a mystery. A singularity, a point where the laws of physics collapse. Now, Einstein knew about this problem, long before the Big Bang theory became mainstream. In fact, when Einstein first applied his theory of general relativity to the entire universe, he discovered something shocking. His equations predicted that the universe couldn't be static. It had to be either expanding or contracting. This was 1917. Nobody had observed the universe expanding yet. Everyone assumed the universe was eternal and unchanging. Infinite space filled with stars, just sitting there, forever. So Einstein looked at his equations and thought, I must have made a mistake. The universe is obviously static. So he added a term to his equations, a cosmological constant, a kind of anti-gravity force that would push outward and balance the inward pull of gravity. With this adjustment, his equations allowed for a static eternal universe. Problem solved, or sort. Then in 1929, Edwin Hubble made a discovery that shattered everything. He observed distant galaxies and found that they were all moving away from us. The farther away they were, the faster they were receding. The universe was expanding. Einstein's original equations had been right all along. The universe wasn't static. It was dynamic, growing, stretching. When Einstein learned about Hubble's discovery, he called adding the cosmological constant his biggest blunder. He had the equations that predicted the expansion of the universe, and he ignored them because they didn't match what he thought reality should be. If he had trusted his math, he could have predicted the expanding universe before anyone observed it. But he didn't, and for the rest of his life, he regretted it. If you're still with me, you're about to learn something that almost nobody talks about. But before we get there, I need you to do something. Subscribe to this channel right now. What I'm about to reveal is going to challenge everything you think you know about existence. And you'll want to see what comes next. Hit that like button too. And if this is making you question reality, share it with someone else. Let's continue. Now, here's where it gets interesting. Once Hubble proved the universe was expanding, physicists started working backward. If the universe is expanding now, that means it was smaller in the past. And if you go back far enough, you reach a point where everything was compressed into an infinitely small space. The Big Bang. But there was another physicist, a contemporary of Einstein, who had a different idea. His name was Alexander Friedmann. And Friedmann took Einstein's equations and found multiple solutions. Not just an expanding universe, not just a static universe, but also a universe that expands, reaches a maximum size, and then contracts back down. A breathing universe. An oscillating universe. One that cycles between expansion and contraction forever. No beginning, no end. Just eternal cycles. Think about what this means. Instead of the universe starting from nothing and expanding forever into heat death, it could be expanding now, will eventually stop, and then contract back into a hot, dense state. And then, instead of collapsing into a singularity and ending, it could bounce, rebound, explode outward again in a new cycle of expansion. This is called the cyclic model of the universe, or the Big Bounce, and it's been around since the 1920s. But it was mostly ignored because the Big Bang model was simpler. It fit the data, and physicists like simplicity. But the cyclic model never went away, it just waited. And now, a century later, it's coming back. Because we're finding evidence that the Big Bang model might be incomplete. Let me show you why the Big Bang has problems. First, the horizon problem. When we look at the cosmic microwave background, radiation, the afterglow of the Big Bang, we see that it's incredibly uniform. The temperature is the same in all directions to within 1 part in 100,000. But here's the issue. According to the Big Bang model, regions of space on opposite sides of the observable universe have never been in contact with each other. They're too far apart. Light hasn't had enough time to travel between them since the Big Bang. So, how did they end up at the same temperature? For two regions to have the same temperature, they need to exchange energy to equilibrate, but they've never been in contact. So why are they the same? The standard answer is inflation. A brief period right after the Big Bang when the universe expanded faster than light, stretching a small, uniform region into the vast universe we see today. Inflation solves the horizon problem, but it creates new questions. What caused inflation? What stopped it? And why did it happen at exactly the right rate to produce the universe we see? Inflation is a patch, a fix added to the Big Bang model to make it work, but it's not a fundamental explanation. Second problem, the flatness problem. The universe is geometrically flat, meaning if you draw a triangle on a cosmic scale, the angles add up to exactly 180 degrees. But for the universe to be this flat now, it had to be incredibly, absurdly flat right after the Big Bang, off by even a tiny fraction. And the universe would have either collapsed back on itself immediately or expanded so fast that no structures could form. The initial conditions had to be fine-tuned to an unbelievable degree. 1 part in 10 to the 60th. That's a 1 with 60 zeros after it. Why? Why was the universe set up so precisely? Again, inflation is offered as an explanation. Inflation stretched out any curvature, making the universe flat. But why did inflation happen? Where did it come from? What set up the conditions for inflation? The Big Bang model doesn't say. It just assumes it happened. Third problem. The singularity itself. At time zero, the Big Bang model says the universe had infinite density and infinite temperature. But infinity is not a physical thing. It's a mathematical breakdown. When your equations give you infinity, they're telling you they don't apply. General relativity breaks down at the singularity. quantum mechanics might take over, but we don't have a complete theory of quantum gravity yet. So we don't actually know what happened at the moment of the Big Bang. We have no physics to describe it. The Big Bang model takes you to the edge of the singularity and then says, we don't know what happened next. That's not a complete theory. That's a theory with a hole in it. Now, let's talk about the cyclic model. In the cyclic model, the universe doesn't start from a singularity. It contracts from a previous cycle. As it contracts, it gets hotter and denser. But instead of collapsing into a singularity, quantum effects take over. At extremely high densities, quantum gravity creates a repulsive force. This force stops the collapse and reverses it. The universe bounces. It rebounds into a new expansion phase. No singularity. No down of physics. Just a smooth transition from contraction to expansion. And this has happened before, many times. The universe we see now is just the latest cycle in an infinite chain of cycles stretching into the past and future forever. This model solves the horizon problem naturally. In the previous cycle, the universe was larger and had more time. Regions that are now on opposite sides of the observable universe were in contact in the previous cycle. They equilibrated then. So of course they have the same temperature now. No inflation needed. The flatness problem also solved. In a cyclic model, the universe doesn't need to be fine-tuned at the beginning because there is no beginning. The universe has had infinite time to reach a flat state through natural processes, and the singularity problem? Gone. There is no singularity, just a bonsi. The cyclic model doesn't need patches. It doesn't need fine-tuning. It's elegant, simple, and it fits the data just as well as the Big Bang model. So why isn't it the mainstream view? Because it has its own challenges. The biggest one is entropy. The second law of thermodynamics says that entropy, disorder, always increases. In each cycle of the universe, entropy should build up. And if the universe has been cycling forever, we should be in a state of maximum entropy by now. Heat death, total disorder. But we're not. We see structure, galaxies, stars, planets, life. So, how can the universe have cycled infinitely many times without reaching maximum entropy? This is the entropy problem. And for a long time, it seemed like a deal breaker. But recent work has shown that there might be ways around it. Some cyclic models propose that the universe gets slightly larger with each cycle. Entropy increases, but the volume of the universe increases faster. So the entropy density, the amount of disorder per unit volume, stays low. The universe resets itself in each cycle, not perfectly, but enough to allow new structure to form. Other models propose that entropy is not a fundamental limit, but an emergent property that behaves differently in quantum gravity. We don't have all the answers yet, but the entropy problem is not necessarily fatal. We're halfway through, and I want to make sure you're locked in for the rest. Because what's coming next is going to blow your mind. But first, hit that subscribe button. Seriously. Wow! This channel is all about uncovering the deepest mysteries of the universe, and you don't want to miss what's next. Like this video, share it, and let's dive deeper. Now, let me tell you about the evidence, the actual observational evidence that's making physicists reconsider the cyclic model. First, dark energy. In the late 1990s, astronomers discovered that the expansion of the universe is accelerating. Galaxies are moving away from each other faster and faster. This shouldn't be happening. Gravity should be slowing the expansion down. But it's not. Something is pushing the universe apart. We call it dark energy, and we have no idea what it is. It makes up about 68% of the total energy of the universe. And here's the thing. Dark energy behaves exactly like Einstein's cosmological constant. the term he added to his equations to make the universe static, the one he called his biggest blunder. Turns out, he wasn't wrong. The cosmological constant is real. It's dark energy. And it's accelerating the expansion. Now, in a standard Big Bang model, this leads to a depressing conclusion. The universe will expand forever, faster and faster, until galaxies are so far apart that they can no longer see each other. Stars will burn out. Black holes will evaporate. The universe will reach a state of cold, empty, eternal darkness, heat death. But in a cyclic model, dark energy doesn't lead to heat death. Instead, as the universe expands and thins out, dark energy could eventually decay or change. The expansion could slow down, stop, and reverse. The universe could start contracting, and the cycle continues. Dark energy, which seems like a death sentence in the Big Bang model, becomes the mechanism for renewal in the cyclic model. Second piece of evidence. Anomalies in the cosmic microwave background. The CMB is the oldest light in the universe. It's been traveling for 13.8 billion years, and when we map it, we see tiny fluctuations in temperature. These fluctuations are the seeds that grew into galaxies. But there are patterns in the CMB that don't quite fit the standard Big Bang model. There's a cold spot, a region that's significantly colder than it should be. There are alignments in the fluctuations that shouldn't exist if the early universe was truly random. Some physicists think these anomalies are just statistical flukes, but others think they might be evidence of something from before the Big Bang, echoes of a previous cycle. If the universe bounced from a previous contraction, there could be remnants. Signatures in the CMB that carry information about what came before. We're not sure yet, but the data is intriguing. Third, quantum gravity theories. String theory loop quantum gravity. These are attempts to unify general relativity and quantum mechanics. And when you apply these theories to the early universe, something interesting happens. The singularity disappears. In loop quantum gravity, for example, the repulsive quantum effects become so strong at high densities that a bounce is inevitable. The universe cannot collapse into a singularity. It must rebound. And this is not speculation. This comes directly from the math. Now, we don't have experimental confirmation of quantum gravity yet. We can't test these theories directly. But the theoretical work is solid. And it strongly suggests that the Big Bang singularity is not real. It's an artifact of using general relativity in a regime where it doesn't apply. When you use the right theory, quantum gravity, the singularity vanishes, and you get a bounce instead. So where does this leave us? Is the universe eternal? Did it have a beginning or not? The honest answer is, we don't know for sure. The Big Bang model works incredibly well for describing the universe from a fraction of a second after the beginning onward, but it breaks down at the beginning itself. The cyclic model offers an elegant alternative that avoids the singularity and solves several problems naturally. But it has challenges of its own. The truth is probably somewhere in between. Or maybe it's something we haven't thought of yet. But here's what's clear. The idea that the universe had a definite beginning, that there was a moment of creation, that time started at a specific instant. That idea is not as solid as most people think. It's possible, but it's not certain. And the more we learn, the more evidence we find that suggests the universe might be far stranger and far older than we ever imagined. Let me bring this back to Einstein. When Einstein added the cosmological constant to his equations, he was trying to preserve a static, eternal universe. He thought the universe was unchanging. He was wrong about that. But he was right about the cosmological constant. It exists. We call it dark energy now. And it's one of the most important discoveries in modern cosmology. Einstein called it his biggest blunder, But it wasn't a blunder. It was ahead of its time. And his equations, even with the cosmological constant, allow for cyclic solutions. Universes that expand and contract forever. He knew about these solutions, but he abandoned them. And for a century, physicists mostly ignored them. But now, they're back, because the data is forcing us to reconsider. And it turns out Einstein's forgotten theory might be closer to the truth than anyone realized.